Yes, we are live now. Please start.
Okay. Good evening, everyone. So, welcome to the live session for the Applied Linear Algebra course discussion for the weeks 1 to 4. So today, unfortunately, Sir won't be able to join with us for the session because he has a personal emergency.
We are live now. Please start.
So, welcome to the live session for the. Good evening, everyone. Just a second. Welcome to the live session. Yeah, so we have Kishore, Anirudh, and Prafula. All of us are TAs for the course. So we'll be going through a few questions from the assignments, 3 of them which we thought might be useful to review because those are commonly found to be confusing. So after that, we'll be opening the floor to questions. So you'll be able to put your questions in the chat box and we'll be answering them later on. So let's get started. So I hope the screen is visible now. Yeah. So initially, we'll be in the first few weeks we covered a lot of things about linear. First, we covered linear independence, about subspaces, and we went on until translates of subspace. So first, we started with in the order of each of the weeks. So in the first week, we had a few questions that we thought might be useful. So this is a question from the first week. So this is a question where we had a given subspace and we had to find another subspace which formed a direct sum with the subspace to form the vector space V. Now, what's the main condition that we have to form a direct sum with another subspace? The two conditions obviously that we have are that the sum of the two subspaces should form the vector space V, and the intersection of the subspaces should be equal to 0. Now, the approach that we're going to be taking is to do basis extension, which means basically I'm going to take this. 1, 2, 4, 1, 1, 0, 2, 3 forms a basis for U, which is, so it's a spanning set and it's obviously linearly independent set. So we're going to extend this basis to basis for V, and the other two vectors that form the basis extension, those are going to be linearly independent of the vectors in U, which means that would form another basis for another subspace, which together forms a vector space, a basis for the vector space V. But because they are linearly independent of each other, you'll have an intersection to be equal to 0. So we'll take the original basis. So we want to be able to find an easy extension to the basis. Now, initially, it isn't very obvious what is the correct extension to this basis. So for that, we'll go along the lines of following Gaussian elimination. So one thing you can remember is whenever you want to see whether vectors are linearly independent or you want to do a basis extension, Gaussian elimination usually makes it much clearer because it gives you an upper triangular form to help you understand what the vector space looks like. So once we've done Gaussian elimination, we see that 0010, 0001 is a simple extension to the basis. So to make it obvious, I think you will be able to understand that if there's no way possible that using these two vectors in this subspace, you'll be able to form this any of these vectors, 0010 or 0001. So these are clearly linearly independent of the two vectors that we already have here. And because of the upper triangular nature of the matrix, we are sure that all of these vectors together form a basis for the vector space V. So we found one way in which you can find W, but this isn't the only way. The subspace W itself is not unique for it to form a direct sum with U. There are multiple subspaces that can satisfy the same condition. So one way you could do this is add one of the vectors that are in the basis of U and add it to any of the vectors in the basis that we found right now, and that would be another subspace. So so these two vectors 1023 plus 0010 gives the vectors in option C 1033. So as you can see, it'll be pretty obvious that none of these with this that 1033 can also not be formed by a linear combination of any of these two vectors, which means this is also a linearly independent combination, which forms another which along with u forms the direct sum to form B. How about the other options? We only found two possible ways. So to make sure that they aren't options that form a direct sum, because 2264 is a vector that it belongs to U. If you sum the two basis vectors of given over here, they form the vector 2264. So option A is clearly incorrect. And 2046, which is simply twice the second vector, which means it belongs to the vector space U, so it cannot form direct sum. So this was a problem where we saw how to extend a subspace to form. We use the approach of extending a basis in order to find another subspace which forms a direct sum with a given subspace. Another topic that we covered in the lectures was another very important topic was about injectivity, and before that we even covered what a linear map itself is. So to review what a linear map is, it's basically a mapping or a function that goes from one subspace, one vector space to another, which satisfies certain properties, and these properties are just additivity and homogeneity. And for a given a linear map, to see whether it is injective, the sufficient condition and necessary and sufficient condition to check for that is to say that null t equals 0. If null t equals 0, it is injective, and vice versa. So let's check each of the options. So the first option, we have x squared p of x. Let's check it for additivity. So t of p of x obviously equals x squared times p1 of x plus p2 of x, which means it equals x squared p1x plus x squared p2x, which is basically t of p1x plus t of p2x, which means it satisfies additivity. It also satisfies homogeneity, which is I think it's quite obvious. So the null t equals 0. So if you want to have t of p of x to be equal to 0, there's no other vector other than p of x equals 0 that maps to 0, because the null t because null t equals 0, it is the map is indeed injective. Let's check the other second option. And the second option, we see x1 to xn is mapped to x2 to xn. So additivity and homogeneity are satisfied. You can easily verify this for yourself. But if you notice that irrespective of the value of x1, the value of the t of x1 to xn is x2 to xn, which means multiple any of these vectors map to the same vector, which means this is injective by definition. We could also look at it from a different way. We could say that x1 comma 0 all zeros, irrespective of the value of x1, belongs to null t. So the map is not injective. So these are the questions for week 1 and 2. Next, I'll be passing on the mic to Anirudh, who will be taking for the next two questions. Oh, sorry. Okay. So we have the third and fourth options are quite easy to check. So x1 to xn and 0 comma x1 to xn. This is obviously uniquely mapped. So it is injective. You can also take the null t approach if you want, because only if the input vector is 0, you're going to get 0 at the output. The last option, it obviously doesn't satisfy additivity and homogeneity, because t of p of x plus q of x equals p of x plus q of x plus 4, and not p of x plus q of x plus 2 as you t of p of x plus t of q of x plus 2 as would be in the other case. Yes. Yeah. So now these are the questions for week 1. We'll be moving on week 1 and 2. Now we'll be moving on to Anirudh.
Yeah, so I'll be presenting two questions with regards to week 3. The first question is basically we have a system of 3 linear equations, and the RHS B1, B2, B3 are given to be variables based upon which the question is held. So we have a few different options which we need to check for. Next. So it's pretty trivial to see that this can be written in the matrix form, where we have 1, 2, minus 3, 4, so on, into x. X will be belonging to the vector space R4, and on the RHS we have the B1, B2, B3. Next. Yeah. So as we know, for finding the solving the linear system of linear equations, we perform the elementary row operations, Gaussian elimination on both LHS and RHS. We end up getting something like this, where we see that there are first two rows are non-zero, while the third row is zero, all zero, which shows that the rank of the LHS matrix is actually 2 and not 3. So we also see that the third row in the LHS matrix is all zero, which means the all zero row multiplied with x will always give 0. So this gives us an idea of what values of B1, B2, B3 are possible for this case. Like if you have B3 not equal to B1 plus 2, B2, the last element of the RHS matrix will be non-zero, while the LHS matrix will necessarily need to be 0. So there will be no x belonging to R4, which will be a solution to the system of linear equations. So we'll not have any solutions due to the last. Next. As we see in the option, we had 2, 1, 3 transpose, which does not satisfy this condition, which basically satisfies B3 not equal to B1 plus 2, B2. So it will have no solution. Next. So as I said, the LHS matrix has rank 2, and we also see that the first two columns of this new matrix of the LHS matrix are actually linearly independent. We see the second element are 0, and in another vector it's 1. So the first two columns are linearly independent, which is clearly visible here. So we can say that the column space of the LHS matrix is actually the span of the first two columns. We also see that the last element is 0. So basically, we will be fully covering the subspace with the last element being 0 in R3 by doing the column space. So irrespective of what B1, B2, B3 are, and if they satisfy B3 equal to B1 plus 2, B2, the RHS vector will definitely be in the column space of the LHS matrix. So we'll definitely have a solution. That is exactly what has been said here. First two columns are linearly independent. Therefore, any B satisfying B3 equal to B1 plus 2, B2 will have at least one solution. Next. And we know by fundamental theorem, we can say number of columns of the LHS matrix is equal to rank plus nullity of the LHS matrix. As we saw, rank is 2 and number of columns is 4. So nullity is definitely 2, which is greater than 0, which means we have a non-trivial null space for the LHS matrix. So as we know, that the solution to this system of linear equations will be any one particular solution to this equation plus the null space, which is actually the translate over the null space. So as the null space is non-trivial, we have infinite number of solutions. So 0, 0, 0 obviously satisfies B3 equal to B1 plus 2, B2. So it also has infinite number of solutions. This is the first question. Next. So the next question is based on intersection of spaces. This can be a little non-trivial to understand at first glance. So we decided to do this. So basically we have two subspaces, W1 and W2, being the span of these vectors. We are supposed to find a vector of the form 1, A, B in the intersection. And they have asked to find A plus A as the final answer. Next. So this is just a convention, like to ease out the writing. V1, V2, V3, V4 are taken this way. So by definition, W1 intersection W2 will be V such that V belongs to span of V1, V2 and span of V3, V4. So basically, then we can, if a vector V belongs to this intersection, then we can definitely be written as a linear combination of V1 and V2, and also a linear combination of V3 and V4. Which means we'll be able to write this equation, which means we basically, in order to solve for A, B, C, D, we can transfer this problem into a system of linear equations type of problem. Because like if we take the V1, V2, V3, and V4 as the columns, next V1, V2, V3, V4 as the columns, then if we find the null space of that matrix, what are we actually doing there? We are basically trying to find a linear combination of the columns such that we'll get a zero vector on the RHS. I'm talking about finding the null space. So basically, we are finding the constants A, B, C, and D such that the linear combination of the columns will be 0. So that is exactly what we are doing. And so each vector in the null space will give us one set of values for A, B, minus C, and minus C. Minus C and minus D because we are taking the C into V3 plus D into V4 to the other side. That's why we are getting the minus. Other than that, it's the same. So we go about the normal task that we usually do, finding the null space. We perform Gaussian elimination. We end up getting the upper triangular form. We see that the first three columns are linearly independent, and we have the three pivots in the first three columns. So the fourth variable x4 will be the free variable, and x1, x2, x3 will be the which are based on which are correspond to the pivots will be the dependent variables. We can take x4 to be 24 for ease of calculation. We get the following three values. We see that there is only one free variable, so we can definitely say that the null space of M will only be the span of this vector minus 12, minus 3, 13, and 24. Next. So that's about it. Yeah, we are almost done solving. Therefore, we can say V W1 intersection W2 will be the V such that V equal to A into V1 plus B into V2 such that A equal to 12 by 3B. This is because, as we saw, null space of M basically is a span of just one vector, which means all multiples of this vector. So basically, the first two elements, minus 12 and minus 3, will just be scaled up and down to get other vectors in the null space. So we can write the intersection this way. And for simplicity, if we take B equal to 1, we'll get W1 intersection W2 to be span of 8, 8, 13, which is the same as span of 1, 1, 13 by 8. So we see that W1 intersection W2 only has one vector such that the first element is 1. Any other multiple of 1, 1, 13 by 8 will have the first element to be something else other than 1. So from there, we can say B is equal to 13 by 8 and A equal to 1. And we therefore get A plus 8B equal to 4. Yeah, this is my question. Next, I'll be handing over the mic to Kishore to do the next one.
Right. Hello, everyone. My name is Kishore, and I'll be handling one of the crucial concepts of week 4 of this course, which is change of basis. So change of basis is one of the crucial concepts of this entire course. And it has tremendous applications in several areas. And it should be one of the major takeaways for you for this course. So it is important that you understand change of basis well. So in my opinion, the biggest obstacle in understanding change of basis is in actually understanding the change of basis matrix to convert from one basis to another. So here is what I use, my method to remember how to construct the change of basis matrix. Different people have different methods to remember, but this is what I use, and maybe this might be useful to you. So we're just going to be considering for now converting to from some non-standard basis to the standard basis. So I've just taken some random numbers over here for the non-standard basis, 503, 127, 879, and constructing the change of basis matrix from this non-standard basis B1 to the standard basis. Once more, from the non-standard basis B1 to the standard basis is you simply take the vectors and put them as the columns of this matrix D. So 503 is the first vector, I put it as the first column. 127 is the second vector, second column, and so on. Next. So now that we have our change of basis matrix from the non-standard basis to the standard basis, let us see how we can apply this. We take a simple example. So if V1 is in the basis B1, the non-standard basis, then to convert it to the standard basis, you simply pre-multiply that vector by D. And then you simply you do the opposite for the next case. If the V2 is in the standard basis, then you convert it to the non-standard basis by taking the inverse of D and pre-multiplying that to V2. So once more, non-standard to standard, pre-multiply by D, standard to non-standard, pre-multiply by D inverse. So keep this in mind because we'll be using this in the next couple of slides. Next. So what we're going to be doing now in these next couple of slides is to revisit the assignment questions 3, 4, and 5 in assignment 4. So I won't have enough space on my slide to actually show you the questions. So feel free to open the SWIAM website. It's the exact same questions. I'll just be discussing them here. So I'll read out the question once more. We have the matrix representation of a linear map T, and that's given by M. Both the input and the output of this M are the standard basis. And the question now is to convert this to a new input basis and a new output basis. We want the new matrix A, which is the matrix representation of the same linear operator T under the new input and the new output basis. Next. All right, so let's apply what we had in the previous slide about converting from non-standard to standard basis. So the new input basis, I've written it out here, 1, 2, 1, minus 1, 2, minus 1, 1, 1, 3. And to convert from this new input basis to standard basis, we know how to do that. Just take the vectors and put them in the columns. Next, same thing we do with the output basis as well. Take the vectors and put it in the columns. So once more, we are converting from the output basis, the non-standard basis, to the standard basis. Next. All right, so now let's actually solve this question. Now we have whatever we need, all the tools we have already established to solve this question. We have P and Q. So, okay, so now let's consider a vector V in the new input basis. Remember that we want this matrix which will convert from the new input basis to the new output basis. So the input vector is going to be obviously in the new input basis, and the vector is V. However, this original matrix M, it only takes the input in the standard basis. So what is the first step? We have to convert from, we have V in the new input basis, and we need to convert that to the standard basis. And we know how to do that. We just pre-multiply by P. This is what we saw in the previous slide, right? And now that PV is going to be in the standard basis, we apply M to it, because M can now take the input since it's in the standard basis. So we apply M. So PV, we apply M to that, it becomes MPV. And this, we know that M will spit out the output in the standard basis, but we want it in the new output basis. So we need to convert now from the standard basis to the new output basis. We know that Q is used to convert from the new output basis to the standard basis. So Q inverse will be used to convert from the standard basis to the new output basis. So we multiply by Q inverse. And then that's it. Q inverse times M times P times V. I'll explain this once more since this is a really crucial concept. V is in the new input basis. We apply P to convert to the standard basis. Apply M because that's the operator. It takes the input in the standard basis. So PV is the new input in the standard basis. Apply M to that. And now convert our output, which is in the standard basis, to our required output basis by multiplying by Q inverse. And notice that we have not put any constraint on V, apart from the fact that this is in the new input basis. So this must be true for any V. So we can finally say that the matrix A, which is our required matrix in the question, should be Q inverse times M times P. You simply have to multiply these things out and you can find that this is the answer. The actual question in the assignment was to find the sum of these values, and I believe that was 5.6. Next. All right, so now the previous question was actually the most tricky one from the questions 3, 4, and 5. Now that we have that, these next two questions are much easier. So the question now is, we have Z, which is 1, 1, 1. It's given in the input in the standard basis, and we have to write it in the new input basis. So next, we know it's quite simple now to convert from the new input basis to the standard basis. We know how to do that. Just take the vectors, put it in the columns. That is P. And just to convert from the standard basis to new input basis, we have to use P inverse. So P inverse times Z will give us the required answer. It's 0.75 minus 0.25, 0. Next. And similarly, we have the question number 5. So now instead of dealing with the input, in question 4, we were dealing with the input. This question is going to ask for the output. So we have a vector K, which is 1, 2, 3, and that is specified in the new input basis. And we are applying T to this. And we want to find the output vector in the standard basis. Next. All right, so now we have two methods of doing it. I'm sure you can actually come up with your own different methods, but this is the two methods that struck me as the most obvious ones. So we first, we know that M has the input in the standard basis and the output in the standard basis. So what we do is we first convert K to the standard basis by multiplying by P. Remember, P converts from the, right. We multiply by P to convert it to the standard basis, right? P converts from the new input basis to the standard basis. So P, we multiply the vector K pre-multiplied by P, and that will convert the vector K to the standard basis. So PK is now in the standard basis, and we apply M to that to get the required output in the standard basis. Next. the other thing that we can do is we can use our result from question 3. So we already know question A from in question 3, the matrix A, right? Matrix A takes the input in the new input basis and spits out the output in the new output basis. So we apply A to K, and then that will give us the result in the new output basis. And finally, we just have to convert to the standard basis by pre-multiplying by Q. Remember, Q converts from the new output basis to the standard basis. And this is pretty much it. We just we took one simple concept, which was converting from the from one non-standard basis to the standard basis, and that's all we had to remember. We can apply the same thing in all of our questions. Next. All right. So until now, we've only looked at converting from either a non-standard basis to a standard basis or a standard basis to a non-standard basis. But what about converting between two non-standard bases? So this was discussed during the lectures also by Professor Andrew. So let's consider a sample problem statement. Consider two bases, B1, which is 1, 2, 2, 1, and B2, 1, 1, 0, 1. And we want to find the change of basis matrix to change this basis from B1 to B2. Next. All right. So method 1 is what Professor Andrew discussed on 2 different occasions during the first 4 weeks. And it is quite simple. You take the aim is to express the original basis B1 in terms of the new basis B2. Express B1 in terms of B2. So what do I mean by that? I have 1, 2. I want to express it as a linear combination of the vectors of B2. So you can see that it is 1, 2 is 1 times 1, 1 plus 1 times 0, 1. And similarly, I do that for the other vector, 2, 1. 2, 1 is 2 times 1, 1 plus minus 1 times 0, 1. And finally, our change of basis matrix is just taking these coefficients 1, 1, 2, minus 1 and putting it as the columns. So from the first 1, 2 is 1 times 1, 1 plus 1 times 0, 1. I take those 2 1s and put it in the first column. And from the second one, I take the 2 and the minus 1 and put it in the second column. However, you might notice that maybe for a 2-dimensional case like this, it must be quite simple to find a linear combination. But what if I go to 3 dimensions or 4 dimensions? It becomes harder to try to find these linear combinations. I can't so easily find these coefficients as 1, 1, 2, minus 1. So instead, let's look at one more method, which is a somewhat simple application of what we've learned so far. So the second method is, the idea behind the second method is to convert to an intermediate basis, which is the standard basis. So we first convert from B1 to standard basis, and then standard basis to B2. So B1 to standard basis, we already know any non-standard basis to standard basis, take the vectors, put it as a columns. So 1, 2 is the first vector, put that as the first column, 1, 2. 2, 1 is the second vector, put it as the second column, 2, 1. Similarly, you do that for B2 as well. B2, the first vector is 1, 1, put that as the first column, 1, 1. The second vector is 0, 1, put that as the second vector, 0, 1. So now we have both the non-standard basis to the standard basis, B1 to S, B2 to S. And finally, we want to convert from B1 to B2, right? So we first convert from B1 to S, that is P. And next we convert from S to B2. So from B2 to S is Q, from S to B2 is Q inverse. So we first apply P to our vector, then we apply Q inverse to that. So Q inverse of P of V. And this should be true for any V, so we can just remove that V, and our final matrix is Q inverse times P. So you can notice how by both methods, we get the same thing. I have not actually explicitly shown the multiplication Q inverse P, but you can just a 2 by 2 case, you can quickly multiply the 2 matrices and check that Q inverse P will give you the same 1, 2, 1, minus 1 as the method 1. All right, so finally, I have a practice question for you. I've taken the 2 bases that we used in assignment 4 questions 3, 4, and 5. It's the same basis. And you should try to convert from basis 1 to basis 2. So you can try, this is a 3 by 3 case, so it may not be very easy to find the linear, the coefficients of the linear depend, writing it in terms of, writing B1 in terms of B2, you have to find the coefficients. Since it's a 3D case, it may not be very easy, but it should not take too long. And you can then try using method 2, which is Q inverse times P, and you can convince yourself that you get the same answer. So many of these questions, you can decide which method you want to do based on your ease of understanding. All right, so that's all that I have to say about the change of basis. Hope this was helpful. This is all which are the crucial concepts from weeks 1 to 4. And we would like to now answer any questions you might have in the chat window. Please do not hesitate to ask any question, even though it might seem trivial to you, it might have some big implications. All right, thanks.
Yeah, if you have any questions, you can type it out in the chat box. Okay, so in case we don't have any more questions, we have a few additional questions that we be able to discuss apart from the questions that we have here. So yeah, we'll move on to that.
Yeah, maybe we can wait for 2 minutes. I
Okay,
see
yeah.
some people responding slowly.
Okay, okay.
Yeah, we'll see for 2 minutes and then carry on.
Sure. In case you found something that we discussed right now to be something unclear, we can revisit that as well.
Okay, maybe we can continue with the additional questions.
Okay.
Yeah. Yeah, so we have some more additional questions on the concepts of week 1 to 4. The first question is on the concept of rank. So we are given that a matrix A, an M cross N matrix A has rank R, and we are asked which of the given options also have the same rank. So next, if we see, okay, there seems to be one question on eigenvalues. I'll just finish this question and come back to the doubt. So yeah, if we see, the row space of a matrix is the span of all its rows, and the column space of a matrix is the span of all its columns. And the rank of a matrix is equal to the dimension of the row space, and is also equal to the dimension of a column space. So if we look at B, next. So if you look at B, it has two A's, one above the other. So each row of A is repeated twice in B. So the row space of B is the same as the row space of A. So rank of B, which is nothing but the dimension of its row space, will be equal to the dimension of row space of A, which is R. So in the next example, if we see, which is we have two A's, one next to the other. So this matrix has each column of A repeated twice. So the column space of C is the same as the column space of A. So the rank of C is the dimension of its column space, which is same as the dimension of column space of A. So it has the same rank as A, which is R. And if we come to the last example, which is D, it has A in the first half and A0 in the second half. So if you consider the part AA, it has a rank of R. It has each row of A repeated twice, so it has rank R. And if we consider the half A0, it also has rank R, but these two parts are linearly independent. From any linear combination of rows or columns from any linear combination of the columns of first part, we cannot get any column of the second part. Similarly, from any linear combination of the columns of second part, we cannot get any column in the first part. So the rank of this matrix D is 2R. So matrices B and C have the same rank R, and matrix D has rank 2R. Now we'll take the question from the chat box. Okay.
The question is, if it is out of scope, can you throw some light on eigenvalues and its physical meaning?
Yes, there's another question before on any shortcut for finding eigenvalues.
Okay, so I'll switch my screen. Okay, yeah. So the question was about like shortcuts to find eigenvalues. What is the exact question?
Yeah.
Yeah,
Is
shortcuts.
there any shortcuts for finding eigenvalues?
Yeah. So one thing that you have to remember about like how we found out eigenvalues, like how we came from the definition of eigenvalues. So basically, if you have a linear map T, then all that the eigenvalues satisfies is t minus lambda I being non-invertible. So if you're able to find any value of lambda, which when subtracted from T gives you a non-invertible matrix, that is going to give you a eigenvalue of the matrix, eigenvalue of the linear map, basically. So this idea, it might be very useful in many cases. For example, let's say let's try to construct a matrix where this is quite useful, even if it's okay. Let's say you have okay. Let's say we made this 4 instead of 0. So although this is a simple case, this is just a demonstration of how that would work out. So when you instantly see this matrix, okay, because it's an upper triangular matrix here, it seems pretty similar, trivial. So given that if you subtract either 2 or 4 from the diagonal of this matrix, so if you have 2 times the identity matrix subtracted from this, or 4 times the identity matrix subtracted from this, you're going to have a column of zeros or a row of zeros. I think it'll be better to show it in 3x3 case. So yeah, if you have something like this, then it should be pretty clear. So you're going to subtract the diagonal elements with a constant value. So if you subtract 2 over here, you're going to have a row of zeros, which is going to make the matrix non-invertible. On the other hand, you can also have a matrix such that if you subtract one of the values, you're going to have 2 identical columns or 2 identical rows. So the core idea here is that you have to have the t minus lambda by I to be non-invertible. There are a few other things that you can check as well. For example, if you have any of the columns or rows to have sum equal to a fixed number. For example, let's say we take so let's say we take this example. So here we have both the rows to be equal to the value 4. So you have 1 plus 3 equals 4 and 2 plus 2 equals 4. So what this means is that you have an eigenvector 1 1. So if you multiply this matrix by 1 1, so what you're going to have is 4 2 plus 2, which is 4 again. So what you see is that when the rows sum up to a fixed value, 1 is going to be an eigenvector of that matrix. So this is just equal to 4 times 1 1. So this is one easy way you can find an eigenvalue of the matrix. If you have both the rows summing, all of the rows, you can extend this to the 3 by 3 case as well. If all of the rows sum to the same constant value, it means that 1 1 is an eigenvector where the sum of the row is equal to the eigenvector. Another interesting case is where you can use another concept that we discussed in the later lectures. This isn't part of week 1 to 4, but still we can discuss that. So if you had the matrix where the columns are equal to a fixed number, for example 2 plus 3 and 1 plus 4. So here the columns are having one as an eigenvector, having the same sum of the columns. What this means is that if you have this equals A, then A transpose would have the eigenvectors of A transpose would be 2, 3, 1, 4, which would mean that the sum of the rows of this matrix would be equal to 5, which means 5 would be an eigenvalue of 8. Yeah, so 5 would be an eigenvalue of A transpose, so which means that it's also an eigenvalue of A. So that's a concept that we saw in the later lectures. So this is another way you can find out eigenvalues of a matrix. I think I've covered quite a few of the methods that we usually do when we look at a matrix. There may be other ways. I may be missing something else. Prof, Kishore,
Yeah, these are the major types. Usually it's more of sort of we just find a way to manipulate the numbers in order to give the eigenvalues. There isn't a solid proper way in which you can easily find eigenvalues. If you want to do very proper way in which you want to find the eigenvalue, then you can do it. Obviously, you can do it using the determinant of A minus lambda I. But that of course will take time, as you need to find the roots of a polynomial equation. So yeah, about finding it easily, these usually the matrix given to you will be something like this. If not, you have to, there is no other way, you have to do the determinant thing only. Also, one other important point here is that eigenvalues and eigenvectors are only defined for operators. Operators are basically linear maps from one vector space to the same vector space. If we take one vector space to some other vector space, then eigenvalues and eigenvectors are not well defined. They are not things that you are not supposed to discuss.
One more small trick is if you have any diagonal element which is part of a row or a column with all zeros, then that will also form an eigenvalue, right? Because it's just a simple application of determinant. We just try to expand the determinant about that row or that column. So for example, this 1, 2, 3, 2, 4, 6, 0, 0, 2. You see that 2 is the only value present on that row. That's a diagonal element, so that will automatically become an eigenvalue. And it doesn't have to be just the last row or anything. It can be any middle row, any middle column also.
Yeah, so basically you're translating the properties of determinants over here. So whenever you see, if you keep in mind the ways in which you can make the determinant 0. So if you start thinking along those lines, you will be able to find the eigenvalues pretty easily. So here, another thing I forgot to mention is here we found just one eigenvalue of this matrix here. So we found that 2 is an eigenvalue. Later, we also discussed the properties of eigenvalues where the sum of the diagonal elements, the trace of the matrix A will be equal to sum of the eigenvalues. So if we had one of the eigenvalues, for example, and we have a 3 by 3 matrix, so here we know that 2 is one of the eigenvalues, and the sum of the diagonal of the matrix is equal to 7, which means the sum of the other two eigenvalues should be equal to 5. So that those sometimes give us good clues about what the other eigenvalues might be.
Also, like in this case, we can actually pretty easily find the determinant as well. It will be 2 into the determinant of the top left 2 into square of the matrix, right? So that's actually pretty easy to find out. That will actually be the product of the eigenvalues. So we have the product of eigenvalues. We also have the sum. We also found that one of the eigenvalues is 2. So we basically have 2 equations and 2 remaining eigenvalues to find. So in this case, pretty easily we can find all 3 without doing the determinant.
Yeah, actually, the first 2 rows are scalar multiples. So
Oh,
0
yeah, right.
would be one eigenvalue.
Oh, yeah, that's another thing I forgot.
So
Yeah, so
using trace, actually, you got the third eigenvalue.
yeah. So the eigenvalues of this matrix are 0, 5, and 2. Okay. Yeah. So maybe to summarize, some of the things that we saw was you can see the sum of a row or column. You can see whether it's invertible or not. You can see what else did we see? Yeah, you basically want to try and make it non-invertible. And finally, you can just use the properties of the eigenvalues. Basically, the summation of the eigenvalues should be equal to the trace of the matrix, and yeah, a determinant equal to yeah, that's maybe another thing you can also use. Maybe determinant of the matrix equals the product of the eigenvalues. This may not be as useful as the others, but sometimes it might be useful. Okay, so have other questions? Can we move on to other questions?
Yeah, there is one question on, is there any practical example where change of basis is used? So as answered by Kishore, yeah, one big usage is where we diagonalize a matrix. So we find a basis with respect to which the operator is diagonalizable. So we change it from the standard basis to this basis of eigenvectors. So that would be one. And also change of basis is just like a translation of the axis or rotation of the axis with their angles intact, which we see in physics a lot when we try to solve problems in mechanics or problems involving dynamics, etc. Yeah.
Yeah, I think quite a few of the applications Professor Andrew covered in the lecture. So, for example, if you wanted to take the power of a matrix, if you're able to express it in the in terms of the eigenvalues and eigenvectors, if you have them, sorry, so yeah, if you're able to find the eigenvalue decomposition of the matrix. So if you want to take the power of the matrix, it's simply going to be taking the powers of the eigenvalues and summing over the same thing. So we use this in I think linear state space equations, and like if you wanted to find the steady state of the system, or you wanted to see whether the system is stable, we checked whether the values of lambda is less than 1 or greater than 1. So if it's less than 1, if you keep applying the same vector a power k onto some vector, we know that it's not going to blow up, because the value of the eigenvalues, if the eigenvalues are all less than 1, then the value of the vector is not going to blow up. So there are a lot of applications like that. So sir discussed about graphs, and there are a lot of applications. So there are some things that maybe we can't elaborate on. There are maybe when you're modeling channels and all that, you'll be able to express different paths for the channel, etc., in terms of the eigenvalue decomposition, and you'll find the most important, the largest eigenvalues to find whether, like the major paths of communication and so on. So that isn't a very accurate description, but it gives you an idea. So the eigenvalue decomposition gives you a sense for what the matrix looks like. So another way to say it is you're getting a linear combination of single rank matrices. So each of these matrices, E1, E1 transpose, E2, E2 transpose, are of rank 1. So if you want to get an approximation of the matrix, then you only have to take the first few largest eigenvalues, so on.
So it's basically like a weighted sum of rank 1 matrices, where you have different weights based on what eigenvalues they have. Like if an eigenvalue, if a particular EI transpose has a bigger eigenvalue, then its contribution to the final matrix will be higher. So if we want to find an approximation, we leave out the smaller eigenvalue components and just take the bigger eigenvalue.
Yeah, sir also later mentioned applications in optimization, where if you wanted to maximize or minimize a quadratic form, we had the maximum value equal to the maximum eigenvalue. So I think that comes in week 8 or something. So yeah, so clearly there are a lot of applications.
The question about the physical meaning of eigenvalues. So I'm not sure exactly what, I can't explain it exactly because that's not my core subject. But in the first year, it's very likely you've learned something about quantum mechanics and the use of Hamiltonian. And over there, you might, your teacher might have told you something about how we can only find the states which are eigenvalue states or something along those lines. So especially in physics and quantum physics, these eigenvalues have tremendous applications.
Yeah. Oh yeah, there's another comment. Eigenvalues will decide how fast or slow the least mean square algorithm converges in applications like optimized control. That's true. In things like gradient descent, the values of the eigenvalues like determine how fast or slow the solution converges. So yeah, almost everywhere you deal with any kind of system, you usually model it as a linear system, which means obviously you're going to deal with either eigenvalues or singular values, no matter what. I think there's a bit of a delay for the YouTube. So we'll have to wait a bit for the questions. Can we move on to the any other question that's there?
Yeah, so there is one question on what is the application of eigenvalue and rank of matrix.
Yeah, eigenvalues, as we said, they basically characterize the system, eigenvalues and eigenvectors. So rank of a matrix, of course it's good to know what the rank of a matrix is. So
the simple application that you can think of is just solving a system of linear equations. It might seem trivial, but the number of places in which you would have to do something like this is just tremendous. In every single field, solving a system of linear equations is a really important part of the application. And rank is checking the rank for whether or not the solution will be unique is one of the main first steps involved.
Yeah.
Yeah, maybe we can go through one more of question now from the additional question.
Okay. I think there's a slight delay to the YouTube thing. So,
Yeah, yes.
anyway, okay. For now, we'll move to the rest of the questions, and then if something else comes up, we'll move back.
Yeah, yes. Yes.
Is it visible now?
Yes, yes. So the next question is on invertibility. So we are given two matrices. Matrix A is a 4 cross 4 matrix with each row being a permutation of the numbers 1, 2, 3, 4. So each row of the matrix A has the numbers 1, 2, 3, 4. And matrix B is another 4 cross 4 matrix where each row is a permutation of the numbers -1, -2, -3, and 6. So we need to decide whether each of these matrices are invertible or not. So if you look at the solution, so each row of the matrix B has the numbers -1, -2, -3, and 6 in any order. Each row will have all these four numbers in some order. So the sum of each row of matrix B is 0. So the vector all ones is in the null space of B, which means rank of the matrix is less than 4. Rank of matrix B is less than 4. So matrix B is not invertible. So any matrix B which has each row as a permutation of these numbers -1, -2, -3, and 6 is not invertible. Now, if we look at the matrix A, which has each row as a permutation of the numbers 1, 2, 3, and 4, in the next slide, we have an example for that. Yeah, so we have given an example where each row has the numbers 1, 2, 3, and 4 in some order. Performing Gaussian elimination on these rows, we get an upper triangular matrix, and we see that the four rows in this upper triangular matrix are linearly independent. So the rank of the matrix A is 4, and hence A is invertible. So we have now seen an example where a matrix has each row as a permutation of the numbers 1, 2, 3, and 4 and is still invertible. So yeah, there exists examples of matrix A which are invertible, but there are no examples of matrix B which are invertible. All matrices B are non-invertible. Yeah. Yeah. So yeah, we still have some time. If you guys have any questions, you can type them in the chat window. Meanwhile, maybe we can proceed to the next question as well. Yeah. Yeah, so the next question we have is on the properties of a determinant. We have said that a matrix A has determinant equal to 2, and matrix B is obtained from matrix A by scaling row 1 of matrix A by the number 5, then adding 3 times row 3 of matrix A to the row 1, and swapping row 2 and row 3. So after you do all these three operations on matrix A in this sequence, what is the determinant of the result in matrix B? So if you look at the solution, we know that scaling a row by a constant multiplies the determinant by the same constant. So scaling row 1 by 5 leads to multiplication of the determinant by 5. And we also know that adding one row to the other, or a linear or a scalar multiple of one row to the other, doesn't cause any change in the determinant. So adding 3 times row 3 to row 1 doesn't make any change in the determinant. And we also know that swapping any two rows causes a change of sign in the determinant. So finally, the determinant of B would be -1 times 5 times determinant of A, which is -10. Yeah, hope this was clear. This is a very simple question. Yeah, and if we look at our final question, it is again related to the solutions of a system of linear equations. We are given a operator from linear map from r power 4 to r power 3, and it is represented in the standard matrix basis by the matrix A shown in this slide. we have to decide whether for any B in R3, does it have infinitely many solutions, and whether T is surjective or injective, and whether a particular B has solutions. So after Gaussian elimination on the rows of A, we get this upper triangular matrix, and from this we see that these three rows are linearly independent. So the rank of A is 3, and we can also see that by a simple calculation, we can also get from this upper triangular form, we can also get that null space of A has dimension 1, and it is equal to span of the vector shown here, minus 61 by 8, 11 by 16, 3 by 4, and 1. So null space of A has dimension 1. So A cannot be injective. And the map T is from R power 4 to R3, and rank of A is 3. So the range of T is the entire codomain R power 3. So the map T is surjective. Map T is not injective, but it is surjective. So since the range of T is the entire codomain R power 3, for any vector in R power 3, any vector in R power 3 lies in the range of T. That means there exists an X in R power 4 for every B in R power 3, such that T times X is B. Now we need to decide whether, so for every B in R power 3, we know that there is at least one solution to the equation TV equals T. We need to decide whether it has infinitely many solutions or unique solutions. So let X and B be such that Tx is equal to B, and let V be a vector such that it is X times some constant into minus 61 by 8, 11 by 16, 3 by 4, 1. This vector minus 61 by 8, 11 by 16, 3 by 4, and 1, it lies in the null space of the operator T. And this constant below is a real number. So there will be infinitely many V's which are of the form X plus C times this vector. So now if we apply the linear map T on V, we get T times X plus C times T into the null space vector, which is again Tx plus 0 equals B. So for every B, there exists infinitely many solutions for the question TV equals B, because C can be any real number. We can take the X that is such that Tx equals B and add any constant times the null space vector to X, so that TV will be B. So for any B in R3, we have infinitely many solutions for the equation TV equals B. Hope this was clear. Yeah.
I think, yeah, we're done with whatever questions we had decided for the session. So yeah, someone has also asked if there are any reference books for working on more problems. Yeah, as Kushal mentioned, the Gilbert Strang's book is obviously a extremely popular book, though I haven't used it myself. But yeah, there are quite plenty of books where you could solve questions. Questions from linear algebra done right, they are pretty good. Like they do test quite a deep understanding of the questions.
As part of this course, the focus in the assignments has mostly been on the numerical style questions, but the textbooks have more of a flavor of proofs and questions along those lines. So we have not actually been able to test this in this course because of our restriction of having to offer it online. But in general, when taught when a linear algebra course is taught, it is common to have almost more than half the questions to be more of proof and the theoretical questions rather than applications. So it is quite important, if you are interested in this topic, to go and look at the proofs involved in many of these concepts. And these are offered in many of the examples of these popular textbooks.
Yeah, so in case anyone has questions from the assignments that are not one of the questions that we discussed, we could clarify on that as well.
So we have some more time left. We are done with all the questions problems we wanted to explain. So all the time is for doubts now. So any doubts you have, you can please type in the chat window.
It can be any problem or even a concept or like whatever. Uh,
This is meant to be more of a discussion. So absolutely anything at all. You may not think it's useful, but it could, it's just, there'll be so many people watching this and someone will find this useful. So don't hesitate to ask. I'll use the short pause to also let you know that we have two coming sessions in the upcoming days for weeks 5 to 8 and 9 to 12. You can expect the pattern of the live sessions to be similar to the ones we have done today. It might be conducted by Professor Andrew or us or both. So we'll be spending some time initially explaining the important concepts of these courses, of these lectures. And after that, we'll be having a question and answer session, just like we have in this chat. So today, most of the questions have come from the chat box in YouTube, but the NPTEL team is also supposed to have given you a Google form in which you're supposed to ask your questions beforehand. So if you have any specific questions from the assignments of these weeks, please write them down. And if you have any feedback related to this, to our live session today, anything you would expect in the next live session, anything at all, please let us know, because this is important to us. We will be looking through this feedback and modifying our explanations and so on. Thanks. Okay, there's a question about CSI or NET. I'm not sure what that is, but I assume it's an engineering exam. This is similar to any of the other linear algebra courses out there. So you can treat this as a strong first level linear algebra course, which covers several concepts.
Yeah, but it's not related to engineering. I think
No.
it is related to pure sciences and math. So yeah, our course is only for mainly targeted towards engineering students to gain understanding of some useful linear algebra concepts which we'll be using in engineering. This is not aimed for pure math students. Yeah. For pure math students, you will be having some courses on NPTEL on linear algebra offered by math departments of IITs and ISC and other universities.
I think there's a question: how to determine injective, surjective, and invertibility when polynomial is multiplied by x or x squared? Okay, I'll move to the whiteboard. Yeah, so this is about the when a polynomial is multiplied by x or x squared. Okay, so the question is, if you have a linear map T of P of x, I'm audible, right? Yeah. Okay. So if you had a linear map set T of P of x equals x squared times P of x, we discussed that in the first question actually, so we'll anyway review it again. So any polynomial, for example, you can take a general, let's say the vector space on which this linear map is operating is a P2 of R, which means it has all the polynomials of degree maximum 2. So the general polynomial in that a vector space would be of the form a0 plus a1x plus a2x squared. So if you multiply x square by this polynomial, what happens? So x square p of x is basically equal to a0 x square plus a1 x cube plus a2 x power 4. Now, yeah, so the range of the polynomial over here is going to belong to P4 of R. So that's sort of the way. So what we want to find out is whether this linear map is injective or not. So that was the question. So what is the condition for injectivity? By definition, injectivity is if you have a linear map if T and if TU equals TV. If TU equals TV implies U equals V, then it means that the linear map is injective. Or equivalently, you can also say if null T equals 0, which means if 0 is the only vector in P2 of R which maps to 0, then the map is injective. So both these two things are equivalent. 1 and 2 are equivalent definitions for injective linear maps. So how about this case here? If you want x square p of x to be equal to 0, which is in this case would be of this form, you'll have for x square p of x to be equal to 0, then you'd have to have all of these coefficients equal to 0. So if this has to be equal to 0, then a0, a1, and a2 all equal to 0, which means that the only polynomial in P2 of R which satisfies which belongs to the null space of T is the 0 vector, the 0 polynomial basically. So is the only, okay, so basically I can say this is basically equal to the null space of T. So because the null space of T equals 0, which is only the 0 element, we've satisfied this condition, which makes it injective. You could think of it in the other way. So for example, if x square p1 of x equals x square times p2 of x, then surely there's no other possibility that if x square p of x p1 of x equals x square times p2 of x, p1 of x has to be equal to p2 of x, which means the linear map is injective. So I hope that is pretty clear. So this is about injectivity. If you want to talk about surjectivity, if you see, I've taken the general polynomial for the domain of the matrix, which is a0 plus a1x plus a2x squared. So any polynomial times x square would give you a polynomial of this form. So if you see here, this does not cover all of the possible combinations of polynomials that you could have in P4R. So P4R consists of all of the polynomials which have degree maximum 1. And clearly this doesn't cover all of them. For example, a naught plus, or
like you could even argue a more simpler point, like in the range, any constant will not be mapped to, like we can't have a polynomial multiplied by x square giving us a constant. That is not possible, because like even if p of x is degree 0, which is basically a constant, the element to which it maps to will be at least degree 2. If degree of p of x is d, then the degree of the polynomial it maps to will be degree d plus 2 for sure. So which means any constant or linear polynomial will never be mapped to, which means obviously range is not equal to the
so for surjectivity, basically the definition is range t equals so the condition for surjectivity is range t equals if the map the linear map maps from t v to w, then if range t equals w, then you can say that it is surjective. So in this case, range t is a subspace of w, which in this case is P4R. So this map is not surjective. So I hope that clarified. If it wasn't clear, please feel free to enter it in the chat box again. Oh, okay. So invertibility. Invertibility is okay. So if you've seen the lectures, so we said that any linear map is invertible if if you want t to be invertible, then it has to satisfy injectivity and surjectivity. So since in our case, in the polynomial multiplied by x square, it is only injective and it's not surjective, so it's clearly not invertible. So yeah, the way to think about invertibility is you have to have, so for example, if this is the vector space V and this is the vector space W and T maps from V to W, for any vector in this space W, you need to have an image in V. So if this is a picture of the linear map that Professor Andrew would have drawn several times in class. So if the vectors in V map to this, which is range T, if range T is not equal to W, it's a subspace of W, in that case, it won't be surjective, which will lead to it not being invertible. So if it's not injective, in a sense, like multiple vectors in V map to the same, for example, if these are two, if two vectors in V map to the same W, which means if you have this vector, you don't know, you don't have a unique map that goes back to V. So injectivity and surjectivity are two necessary conditions. I mean, they're actually the definition of invertibility. So yeah, I hope that clears it.
In a more intuitive sense, it's basically like if you take a linear map, it is actually a function, right, from one set to another. So we just, while doing, if we want to find the inverse, we basically want to reverse all the mappings. So if it's not surjective, then there will be elements in W which will not map to any elements in V. Like definition of a function is that its domain, all vectors in its domain should be mapped to something else, right? So that won't be the case here. That's why surjective is a necessary condition. And again, injective also is a necessary condition because we can't have one element in W mapping to multiple elements of B while taking the inverse. So that is why the invertibility condition in a more intuitive sense actually requires both of them to be true. If either of them are not true, you'll have some issue like this.
Deepak has confirmed that it's clear.
Okay, I think, yeah, if there are no more questions, maybe we can meet in the next session. Yeah, you'll be getting an announcement in NPTEL and Swayam from on when the next sessions are going to be. Yeah. So yeah, we'll wait for 1 or 2 minutes more, and if there are no more questions, we'll close the session for today.
One more reminder to please fill your questions in the Google form, because that will be influencing what are the content in the coming sessions. So if you have any specific questions, then you can put it in the form beforehand, and we'll be much more prepared to answer those. And if you have any feedback about today's session as well, then please add that too. Thanks.
I thought I'd mention just one more thing about like injectivity, searchability of matrices. I think this sir had discussed this in class, but I just thought I'd point it out. If you have a matrix where you have either a tall matrix or a fat matrix. So if you have a fat matrix, you have m to be less than or equal to n, which is the number of rows to be less than or equal to the number of columns. So in this case, the map is not injective, because in this if you look at this matrix, it will have it has only it can have only two linearly independent columns. The rank of the matrix is basically will be equal to 2, which means by the fundamental theorem of linear maps, the null will be greater than 0, which means it will be not injective. And in the case where it's tall matrix, you're going to have so the range of this matrix is basically the column space of this matrix. So the call space is going to be having only two linearly independent vectors, which means the range is so the dimension of range, dimension of call space equals 2, but according to the fundamental theorem, dim v equals 3. So the dimension of null of this matrix will be equal to 1, which is greater than 0, which means it's non-surjective. Sorry, that's not what I meant. So the range T is not equal to W, which means it's not surjective. So in both cases where it's a fat matrix or a tall matrix, it's clear that you can't have any inverse. So that's why we have inverses only for operators.
May not be necessarily operators. Like we basically have inverses for cases where the domain and codomain, that is the two vector spaces from which V and W, basically the two vector spaces have the same dimension.
Yeah, so that's what we called in the lecture. We called it an isomorphism. So if two vector spaces have the same dimension, you can have a linear map between them that is invertible. So yeah, so in this case, obviously, if you have a tall matrix or a fat matrix, the dimension of V and W are different, which means it can't be an isomorphism. So they can't be any invertible linear map. It's just that this intuitive understanding of, like, once you see a tall matrix or a fat matrix, you want to instantly, like, remind yourself about whether it's injective or surjective, and yeah, things like that. Because sometimes you'll be having systems where you'll have a tall matrix or a fat matrix, for example, and you want to get an idea about what the solutions look like. You might have infinite solutions, you may have no solution, and so on. So having an intuitive understanding of all of these things are pretty useful. Yeah, so if there are no more questions, we can, I guess, close. I hope this session was useful for everyone. Yeah, sorry for, I guess, poor handwriting, but I'll try practicing on it more. So in case you have any feedback, please make sure you put it on the Google form. Could be about anything.
Meet you all in the next session, I guess.
Okay. Okay. Yeah. Thanks a lot for joining.